A proportional integral derivative controller is a control loop feedback mechanism commonly used in industrial control systems. A PID controller continuously calculates an error value as the difference between the measured process variable and a desired set point. The controller attempts to minimize the error over time by adjustment of a control variable, such as the position of a control valve, a damper, or the power supplied to a heating element, to a new value determined by a weighted sum, where and all non-negative denote the coefficients for the proportional, integral, and derivative terms, respectively. In this model, P accounts for present values of the error, I accounts for past values of the error, and D accounts for possible future values of the error, based on its current rate of change. As a PID controller relies only on the measured process variable, not on knowledge of the underlying process, it is broadly applicable. By tuning the three parameters of the model, a PID controller can deal with specific process requirements. The response of the controller can be described in terms of its responsiveness to an error, the degree to which the system overshoots a set point, and the degree of any system oscillation. The use of the PID algorithm does not guarantee optimal control of the system or even its stability. Some applications may require using only one or two terms to provide the appropriate system control. This is achieved by setting the other parameters to 0. A PID controller will be called a PI, PD, P or I controller in the absence of the respective control actions. PI controllers are fairly common, since derivative action is sensitive to measurement noise, whereas the absence of an integral term may prevent the system from reaching its target value. For discrete time systems, the term PSD, for proportional summation difference, is often used. History and applications. PID controllers date to 1890s governor design. PID controllers were subsequently developed in automatic ship steering. One of the earliest examples of a PID-type controller was developed by Elmer Sperry in 1911, while the first published theoretical analysis of a PID controller was by Russian-American engineer Nicholas Minorsky. Minorsky was designing automatic steering systems for the U.S. Navy, and based his analysis on observations of a helmsman, noting the helmsman controlled the ship based not only on the current error, but also on past error as well as the current rate of change. This was then made mathematical by Minorsky. His goal was stability, not general control, which simplified the problem significantly. While proportional control provides stability against small disturbances, it was insufficient for dealing with a steady disturbance, notably a stiff gale, which required adding the integral term. Finally, the derivative term was added to improve stability and control. Trials were carried out on the US New Mexico, with the controller controlling the angular velocity of the rudder. Pi control yielded sustained yaw of plus or minus 2 degrees. Adding the D element yielded a yaw error of plus or minus 1/6 of a degree, better than most helmsmen could achieve. The Navy ultimately did not adopt the system, due to resistance by personnel. Similar work was carried out and published by several others in the 1930s. In the early history of automatic process control, the PID controller was implemented as a mechanical device. These mechanical controllers used a lever, spring and a mass and were often energized by compressed air. These pneumatic controllers were once the industry standard. Electronic analog controllers can be made from a solid-state or tube amplifier, a capacitor and a resistor. Electronic analog PID control loops were often found within more complex electronic systems, for example, the head positioning of a disk drive, the power conditioning of a power supply, or even the movement detection circuit of a modern seismometer. Nowadays, electronic controllers have largely been replaced by digital controllers implemented with microcontrollers or FPGAs. However, analog PID controllers are still used in niche applications requiring high bandwidth and low noise performance, such as laser diode controllers. Most modern PID controllers in industry are implemented in programmable logic controllers or as a panel-mounted digital controller. PID temperature controllers are applied in industrial ovens, plastics injection machinery, hot stamping machines and packing industry. Control loop basics. A robotic arm can be moved and positioned by a control loop. By applying forward and reverse power to an electric motor to lift and lower the arm, it may be necessary to allow for the inertial mass of the arm, forces due to gravity, and to correct for external forces on the arm such as a load to lift or work to be done on an external object. The sensed position is the process variable. The desired position is called the setpoint. The input to the process is the output from the PID controller. It is called either the manipulated variable or the control variable. The difference between the present position and the setpoint is the error, which quantifies whether the arm is too low or too high and by how much. By measuring the position, and subtracting it from the setpoint, the error is found, and from it the controller calculates how much electric current to supply to the motor. The obvious method is proportional control. The motor current is set in proportion to the existing error. A more complex control may include another term, derivative action. This considers the rate of change of error, supplying more or less electric current depending on how fast the error is approaching zero. Finally, integral action adds a third term, using the accumulated position error in the past to detect whether the position of the mechanical arm is settling out too low or too high and to set the electrical current in relation not only to the error but also the time for which it has persisted. Over time the steps accumulate and add up dependent on past errors. This is the discrete time equivalent to integration. Applying too much impetus when the error is small and is reducing will lead to overshoot. After overshooting, if the controller were to apply a large correction in the opposite direction and repeatedly overshoot the desired position, the output would oscillate around the set point in either a constant, growing, or decaying sinusoid. If the amplitude of the oscillations increase with time, the system is unstable. If they decrease, the system is stable. If the oscillations remain at a constant magnitude, the system is marginally stable. In the interest of achieving a controlled arrival at the desired position in a timely and accurate way, the controlled system needs to be critically damped. A well-tuned position control system will also apply the necessary currents to the controlled motor so that the arm pushes and pulls as necessary to resist external forces trying to move it away from the required position. The set point itself may be generated by an external system, such as a PLC or other computer system, so that it continuously varies depending on the work that the robotic arm is expected to do. A well-tuned PID control system will enable the arm to meet these changing requirements to the best of its capabilities. If a controller starts from a stable state with zero error, then further changes by the controller will be in response to changes in other measured or unmeasured inputs to the process that affect the process, and hence the PV. Variables that affect the process other than the MV are known as disturbances. Generally, controllers are used to reject disturbances and to implement setpoint changes. A change in load on the arm constitutes a disturbance to the robot arm control process. In theory, a controller can be used to control any process which has a measurable output, a known ideal value for that output and an input to the process that will affect the relevant PV. Controllers are used in industry to regulate temperature, pressure, force, feed, flow rate, chemical composition, weight, position, speed and practically every other variable for which a measurement exists. PID controller theory. This section describes the parallel or non-interacting form of the PID controller. For other forms please see the section Alternative Nomenclature and PID forms. The PID control scheme is named after its three correcting terms, whose sum constitutes the manipulated variable. The proportional, integral, and derivative terms are summed to calculate the output of the PID controller. Defining as the controller output, the final form of the PID algorithm is where proportional gain, a tuning parameter, integral gain, a tuning parameter, derivative gain, a tuning parameter, error, set point, process variable, time or instantaneous time, variable of integration, takes on values from time 0 to the present. Equivalently, the transfer function in the Laplace domain of the PID controller is where complex number frequency proportional term. The proportional term produces an output value that is proportional to the current error value. The proportional response can be adjusted by multiplying the error by a constant Kp, called the proportional gain constant. The proportional term is given by a high proportional gain results in a large change in the output for a given change in the error. If the proportional gain is too high, the system can become unstable. In contrast, a small gain results in a small output response to a large input error, and a less responsive or less sensitive controller. If the proportional gain is too low, the control action may be too small when responding to system disturbances. Tuning theory and industrial practice indicate that the proportional term should contribute the bulk of the output change. In a real system, proportional-only control will leave an offset error in the final steady-state condition. Integral action is required to eliminate this error. Integral term. The contribution from the integral term is proportional to both the magnitude of the error and the duration of the error. The integral in a PID controller is the sum of the instantaneous error over time and gives the accumulated offset that should have been corrected previously. The accumulated error is then multiplied by the integral gain. Derivative term. The derivative of the process error is calculated by determining the slope of the error over time and multiplying this rate of change by the derivative gain Kd. The magnitude of the contribution of the derivative term to the overall control action is termed the derivative gain Kd. The derivative term is given by derivative action predicts system behavior and thus improves settling time and stability of the system. An ideal derivative is not causal, so that implementations of PID controllers include an additional low-pass filtering for the derivative term to limit the high-frequency gain and noise. Derivative action is seldom used in practice though, by one estimate in only 25% of deployed controllers, because of its variable impact on system stability in real-world applications. Loop tuning. Tuning a control loop is the adjustment of its control parameters to the optimum values for the desired control response. Stability is a basic requirement, but beyond that, different systems have different behavior, different applications have different requirements, and requirements may conflict with one another. PID tuning is a difficult problem, even though there are only 3 parameters and in principle is simple to describe, because it must satisfy complex criteria within the limitations of PID control. There are accordingly various methods for loop tuning, and more sophisticated techniques are the subject of patents. This section describes some traditional manual methods for loop tuning. Designing and tuning a PID controller appears to be conceptually intuitive but can be hard in practice. If multiple objectives such as short transient and high stability are to be achieved, PID controllers often provide acceptable control using default tunings, but performance can generally be improved by careful tuning, and performance may be unacceptable with poor tuning. Some processors have a degree of nonlinearity, and so parameters that work well at full load conditions don't work when the process is starting up from no load. This can be corrected by gain scheduling. Stability. If the PID controller parameters are chosen incorrectly, the controlled process input can be unstable, i.e., its output diverges, with or without oscillation, and is limited only by saturation or mechanical breakage. Instability is caused by excess gain, particularly in the presence of significant lag. Generally, stabilization of response is required and the process must not oscillate for any combination of process conditions and set points, though sometimes marginal stability is acceptable or desired. Mathematically, the origins of instability can be seen in the Laplace domain. The total loop transfer function is where PID transfer function, plant transfer function. A system is called unstable where the closed loop transfer function diverges for some. This happens for situations where, typically, this happens when with a 180-degree phase shift. Stability is guaranteed when for frequencies that suffer high phase shifts. A more general formalism of this effect is known as the Nichols stability criterion. Optimum behavior. The optimum behavior on a process change or setpoint change varies depending on the application. Two basic requirements are regulation and command tracking. These refer to how well the controlled variable tracks the desired value. Specific criteria for command tracking include rise time and settling time. Some processors must not allow an overshoot of the process variable beyond the set point if, for example, this would be unsafe. Other processes must minimize the energy expended in reaching a new set point. Overview of methods. There are several methods for tuning a PID loop. The most effective methods generally involve the development of some form of process model, then choosing P, I, and D based on the dynamic model parameters. Manual tuning methods can be relatively time-consuming, particularly for systems with long loop times. The choice of method will depend largely on whether or not the loop can be taken offline for tuning, and on the response time of the system. If the system can be taken offline, the best tuning method often involves subjecting the system to a step change in input, measuring the output as a function of time, and using this response to determine the control parameters. Manual tuning. If the system must remain online, one tuning method is to first set in values to 0. Increase the until the output of the loop oscillates. Then this should be set to approximately half of that value for a quarter amplitude decay type response. Then increase until any offset is corrected in sufficient time for the process. However, too much will cause instability. Finally, increase, if required, until the loop is acceptably quick to reach its reference after a load disturbance. However, too much will cause excessive response and overshoot. A fast PID loop tuning usually overshoots slightly to reach the set point more quickly. However, some systems cannot accept overshoot, in which case an overdamped closed-loop system is required, which will require a setting significantly less than half that of the setting that was causing oscillation. Ziegler-Nichols method. Another heuristic tuning method is formally known as the Ziegler-Nichols method, introduced by John G. Ziegler and Nathaniel B. Nichols in the 1940s. As in the method above, the end gains are first set to 0. The proportional gain is increased until it reaches the ultimate gain, at which the output of the loop starts to oscillate, and the oscillation period are used to set the gains as shown. These gains apply to the ideal, parallel form of the PID controller. When applied to the standard PID form, the integral and derivative time parameters are only dependent on the oscillation period. Please see the section, Alternative Nomenclature and PID Forms. PID tuning software. Most modern industrial facilities no longer tune loops using the manual calculation methods shown above. Instead, PID tuning and loop optimization software are used to ensure consistent results. These software packages will gather the data, develop process models, and suggest optimal tuning. Some software packages can even develop tuning by gathering data from reference changes. Mathematical PID loop tuning induces an impulse in the system, and then uses the controlled system's frequency response to design the PID loop values. In loops with response times of several minutes, mathematical loop tuning is recommended, because trial and error can take days just to find a stable set of loop values. Optimal values are harder to find. Some digital loop controllers offer a self-tuning feature in which very small setpoint changes are sent to the process, allowing the controller itself to calculate optimal tuning values. Other formulas are available to tune the loop according to different performance criteria. Many patented formulas are now embedded within PID tuning software and hardware modules. Advances in automated PID loop tuning software also deliver algorithms for tuning PID loops in a dynamic or non-steady state scenario. The software will model the dynamics of a process through a disturbance, and calculate PID control parameters in response.